Yo, what is up guys? So today I'm gonna bring you guys another video about data structures, and today I want to talk about undirected graph. And on top of being undirected, this will be unweighted, so there are no weights in this graph. So basically, this is a usual graph representation. So this is a undirected graph and unweighted graph. This means that if you take a look here, what are the main graph elements? We have the nodes. These are the nodes or vertices, and we have the edges or connections between nodes. And uh, on different graphs, you have different graphs implementations. So if you have a directed graph, uh, the edges, they have a direction. For example, if A were connected to E with direction from A to E, E would not be connected to A because this is unidirectional. It would be unidirectional. In this case, it's bidirectional. So you can either go from A to E or E to A because there is a connection between E and A. There's no direction specific that hinders you from going from A to E or E to A. This is you can go either way here. And meaning the unweighted part means that the graph edges and connections, they have no weights, meaning that all the distances are equal within it, each node. So the same from going from A to D is the same cost for as going from A to E or A to F or A to B, and etc. So this is just going to be a simple explanation of how you can build your own unweighted, undirected graph. But you can simply add weights by adding another variable called weight in your structure that we're going to create. And if you want to create a direction, you can also create another variable for the direction, so to specify from where the connection is going to, and change a little bit on how you're going to implement the connect node method that we're going to implement. But anyway, this is the usual graph representation. You have nodes or vertices and edges or connections, and the nodes represent a certain place or a certain spot you want to get to, and edges represent the connections between each spot. So you can go from A to E directly, but you cannot go from A to H directly. You have to either go A to B and then to H, or A to B to F and H, or A to F and H. There's no direct connection between A to H. But I think you're going to be familiar. I think if you're watching this video, you're already familiar with what a graph is. But I tried to introduce in a simple way, explaining what the graph we're going to implement will look like. So this is the graph we're going to implement in our example. And you have here a simple explanation of what is the undirected graph. So we're going to implement it using linked lists, and we're going to have two linked lists. So one linked list will hold pointers to other linked lists, and each linked list will be that has a pointer to it will be representing the node and its connections. So if you take a look here, this is the exact same graph representation using linked lists. So this graph and this graph are equivalent. These two representations are equivalent. This means that you're gonna have the nodes. So every first element from the linked list you have a pointer to will be the head, and will represent a node in the graph. So A is a node in the graph, B is a node in the graph, etc. up to H. So from A to H, these are nodes in the graph. So these represent the nodes, and every single element that comes after a node or comes after the head of the linked list will represent the connections it has. So A is connected to B, D, E, F, and G. So if you take a look here, A is connected to B, D, E, F, and G, but it's not connected to H or C, as you can see here. The same thing applies to B. So B is connected to A, C, F, G, and H. B is connected to A, to C, to F, to G, and to H. And if you take a look here, C is only connected to B. So C is only connected to B. D is only connected to A, and E is also only connected to A. So both D and E are only connected to A. So I guess this is cleaner to see than this, but anyway, it's the same thing. And F is connected to A, B, G, H. F is connected to A, B, G, and H. And G is connected to A, B, F. So G is connected to A, to B, and to F. And H is connected to B and F. So H here is only connected to B and to F. So this is how we're going to represent our graph using linked lists. And we're going to implement some functions. So these are the main functions we're going to use to implement this graph and this graph representation. So PrintGraph will print us this structure here from A to H and onwards. And AddNode will be the method that we're going to use to add a node, meaning that we're going to create a pointer and create a head of a linked list. So if we were to add the node I in this graph, we would create a graph pointer 9 here, pointing to the linked list I that currently has no connections because we just introduced the element in the graph, but the vertex to the graph, but we haven't connected it to anything yet. We have the connect nodes. This method will connect to nodes. So if you want to create a connection between A and C, we would add to the end here a connection to C, and C here we would add a connection to A. Remove connection, we would basically, if you want to remove a connection from A to G, and from we would also have to remove from G to A. So we would delete G and delete A from here, and A would no longer be connected to G, and G would only be connected to B and F, and etc. So remove node, we will completely delete this node. For example, if we want to remove the node A, we would delete the node and all the connections, and not only from the A node, where we have to go through every other node on the graph that has a connection to A and delete A, because A is no longer part of the graph. And we have the FreeGraph method. So this will basically delete the whole graph and leave us with a clean, we'll clean all the memory we've allocated to create the graph, and will leave us with an empty graph pointing to null. And these will be the helper methods we're going to use, so print linked lists to help us in the print graph, because if we want to print a graph, we want to iterate through each of these, and then iterate through each of these. So we want to print this. So we're going to iterate through the linked lists in every pointer from the graph. The init linked list, meaning that we're going to initiate a linked list creating a head pointer here. So every time we're going to use this method in the AddNode. And init graph node, when you want to create the AddNode, but the graph is currently empty. So these are the methods we're going to implement, or the functions we're going to implement. And this, I will go through each step, showing how the graph would look like in the visualization after we add node A, if we add node B, and then add node C, D, E, F, G, and H. Of course, we only added the nodes. There are no connections between the node, and then now we have to create the connections between the nodes. So if we create a connection between A and B with the method ConnectNodes, we would have the first connection, and so forth and so on. So A to D, A to E, A to F, A to G, B to C, B to F, B to G, B to H, F to G, and F to H. And this will be the last representation. This is the complete graph in the visualization. And this behavior will be reflected exactly the same way. I put here in a similar way, but this is exactly the same way in our linked list. The only difference is that once we add a node, in the connect nodes, we'll have a slightly different understanding of what we have to do. But so once we call AddNode, we're going to create a pointer, or initialize a pointer in the graph that points to a linked list that we have to initialize. And then once we add node B, we do the same thing. So these will be pointing to this. So these will be pointing to this. That will be pointing to this, because this graph here is also a linked list. And then if we add node C, node D, E, F, G, and H. Now, if we want to add a connection between A and B, we would have to go to the head node that holds the value A and add B to the end, and go to the head node holding the value B to add the connection to A, because as this is an undirected graph, once we add a connection between one node and the other, we have to add the connection between the second node and the first one, because it's you can go either way. So that's why. So this is connection between A and D, E and A and E, A and F, A and G, B and C, F and B and F, B and G, B and H, F and G, and last but not least F and H. And this is the final graph representation. So this is how we're gonna develop our graph data structure, and I'm gonna walk through the whole coding session. We're gonna code it together. So let's hop onto the file and start coding, so you can better understand what we're gonna do and how you can implement this logic using the C programming language. So now let's hop onto the file here. So I've created a file called undirectedgraph.c, and in here, let's start by including some libraries. So let's first include stdio for printing, and stdlib for mainly for malloc in this case. First thing I want to do is I want to create the two structures we're going to use. So they're going to be two linked lists, but one is going to hold character values and one is going to hold another linked list, or a pointer to another linked list. So let's first create a typedef struct here, node. In this case, we're going to hold a character value and a pointer to the next node. And let's call it linked list, like so. And the second structure will be pretty similar. Typedef struct, and let's call it node G. We can call it node if you want to, but just to differentiate, this is going to be the graph, the node, the the nodes in the graph, so the graph nodes, and this will hold a pointer to another linked list. I'll call it node name because we're pointing directly to the head, and the head is the node name. You can find a better name, I'm pretty sure, but let's stick with node name in this case, and struct node g. So we have a pointer to the next node in the graph. So a pointer to the next structure that holds a pointer to another linked list, and let's call it ugraph. So this is the undirected graph. The U stands for undirected, and I want to start off this video by doing creating the whole main function first, because it's going to be a pretty long main function, and I know what I want to do in the main function because I have the preset names from the slides here, the functions we want to use, right? So if you go back here to the functions where we define the functions, we know the function names we're going to need to create, and we know the prerequisites to what arguments these functions will receive. So I'm going to create the whole main function first, and then I'm going to comment out the lines from the nodes that I'll comment out the lines that we're not going to test first, and we're going to uncomment the lines and test it after we create the functions, so we can test them and have the main function ready to go. So I want to get rid of the main function first because it's just a template, right? What I want to do in the main function is I want to create the whole graph and test out edge cases we have to treat. And I'll talk about these edge cases once we start creating the main function. So if you don't want to watch the main function creation and you just want to watch the creation of the functions itself and the explanation on how we're going to create these functions, you can skip this part here. I'll leave the timestamps in the description down below. But if you want to understand why we're creating this main function the way we are, just stick to this section. It's going to be a little long, but I guess it's pretty important for you to understand what we're doing here. So if you can, stick to it. Otherwise, you can skip it. So let's hop onto the creation of the main function. So let's create a function main. You can create your argc and argv here, but they will not make any difference here because we're not going to use this. So let's first define our undirected graph. Let's call it ugraph and name it graph, and this is a pointer, right? So the pointer to our graph, and let's start it off by pointing it to null. And first thing I want to test is printing the graph when it's null, because I want to have the edge case when we print the graph when it's null, it has to print that the graph is null, so it hasn't been initialized. There are no nodes in the graph, so printing the graph before adding any nodes. And here we're going to print graph, and we're going to pass graph. Next step, we want to start adding the values to the graph. So adding values to the graph. Okay. And let's print here. Oh, sorry. Forget the comment. Sticks to the next line. So let's print here that we're going to add values. So printing graph after adding first node. So printing graph after adding the first node. And the first node will be A. And I want to print node A, B, and C, and then I'll add the list of the other nodes that are missing, so D, E, F, G, and H, and then print it afterwards. So just you can at the beginning of the AddNode function, you can see how we're adding the functions, how the nodes are being added to the graph, and how the graph is slowly increasing in size. So let's first here add node and the node to the graph by reference, because we're gonna mess with the values in the pointer structure here. So that's why we're passing it by reference, so we don't have to return anything from this function. And let's pass in the name of the node we're going to add. So this is node A, and after that let's print graph. Let's just copy this whole line here, or these 3 lines, and this will be node B, node C, and I'll also add here node C again, because as I stated before, we want to treat some edge cases, and one of these edge cases is when we try to add a node that already exists in the current graph. We cannot do that. We cannot allow that, because it doesn't make any sense having 2 nodes that are the exact same, so you cannot differ between them and differ from which one is connected to which, and that's why the node names in the graph have to be unique. So that's why we will not be allowing duplicate in the node names in the graph. So let's just, in the last one here, let's printing graph after trying to add printing graph after trying to add already existing node C. So this is when we try to add a node that already exists. And before here, we're going to add nodes. So node A, node B, and here B. So we're going to add node A, node B, node C, and we're going to try to add a node C that already exists in the graph. So we have to print something telling that node already exists in the graph. And now I just want to add the missing nodes. So after adding nodes, in this case will be node D, E, F, G, and H. So now let's just copy this line and D, E, F, G, and H. From top here, this will be D, E, F, G, and H. So now that we have added all the nodes in the graph, they're not connected. So we're in the state of the graph where the graph looks like this. So we're going to add node A, B, C, D, E, F, and G, and H. So this is our current state of the graph. It has no connections, but it has nodes. So each node is isolated from each other. Now we have to add the connections between the nodes so we can actually understand and reach a state of the graph where we add connections. So the first connection we want to add is connection from A to B. So let's print this. So printf, adding a connection between nodes, say here, node A and B. And now we're going to use our function called ConnectNodes. We're going to pass in our graph A and B. And I'm not passing it by reference because we're not changing the pointers in our graph linked list. We're changing the linked list that our pointer points to. So there's no need to pass the graph by reference. And after that, I want to print the graph just so we can see that our graph will have this connection here. Next up, A and D. But before that, I want to create a virtual connection that doesn't exist in our current graph. So I want to create a connection between A and C that will not be present at the end of the code. Our complete graph will not have the connection between A and C, and this is because I just want to test the RemoveConnection function, and I'll create a connection that doesn't exist in the current graph, so we can remove it later on and test the RemoveConnection function. So now let's just copy this and add a connection between A and C and let's try to add a connection between A and K, and K is not present in the current graph, so K does not exist in current graph. So we can also test an edge case where you cannot add a connection between a node and another node that is not in the current graph. All the nodes have to be in the graph, and the nodes must not be connected in the first place so you can create a connection. So we're testing the edge case where we're trying to connect a node to a node that is not in the graph. Okay, so K is not in the graph. And now let's just add the connection let's just finish adding the connections. So A will be connected to D, E, so D, E, F, G. So as you can see here, we'll be adding the connection D, E, F, and G. So this will be A to D, E, F, and G. And D, E, F, and G. A is not connected to H, okay? So I guess we're good up to now. Next, let's test the edge case where we try to connect a node that is already connected, or two nodes that are already connected to each other. So in this case, A is already connected to E, right? So if you try to connect A to E again, it shouldn't be allowed, okay? The reason being, there's no need to create two connections between two nodes, right? They're already connected, right? So it cannot allow two connections. So you will not know how to different one connection to one connection or the other, right? So that's why it doesn't make any sense having two connections between two nodes. You cannot allow that. So let's try adding. Oh, sorry. Let's copy this. Print this here. Print graph, just so you can see that these connections won't be added. And trying to add a connection that already exists. So let's rephrase this. Trying to add a connection that already exists, and this will be between A and E. This A to E. Okay, so now we're good, and we're trying to connect A to E, and of course, this shouldn't be allowed. Next up, trying to add a connection. Oh, yeah, I think this is the last edge case up to now. So now let's finish adding up the or connecting the B nodes. So let's connect B to C, and then B to F, B to G, and then B to H. And let's just copy this. It is the same amount of elements, but in this case it's B connected to C, F, G, and H. C, F, G, and H. And this will be B, 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 H, G, F, and C. Okay? And last but not least, let's add the connections between F and G. So F and G, and F and H. So F and G. Oh, sorry. F and G, and F and H, right? So F and G and H. Let's just delete this. Oh, sorry. So adding connections between F, G, and H. And G. Let's add a comma here. Formatting doesn't actually matter. So, okay. So next up, I want to try removing a connection. So let's test the RemoveConnection function. That's why we added connection between A and C that doesn't exist in the graph. So we can now test the remove connection from A to C. So let's print here that we're going to remove the connection. Removing the connection between nodes A and C. And we're going to use the function called RemoveConnection. We're going to pass the graph A and C. And we also going to print the graph so we can see that the connection has been removed. So let's print the graph here. Next, let's try to remove a connection from a node and a node that doesn't exist, because we're not allowed to remove a connection between a node A and a node K that doesn't exist. So let's also try to removing the connection between nodes. In this case would be node A and K. And K does not exist in the current graph. And here, well, let's just format the file. And in here, we're going to remove connection, and remove connection will be between in the graph and between A and K. Okay, and this will print that this cannot be done because K does not exist in the current graph. Now, the last thing we have to do is, now our graph is complete, right? So we have our full graph. So at this point, this is the representation of our graph. And now let's just try to test our last function, and this will be the FreeGraph. And we're gonna print the state of the graph after we free each of these nodes, so you can clearly understand how the remove of all, because we still have to test the remove node, right? And the remove node will use the remove connection, because we want to clean out connections, and then we're going to remove a node completely from the graph, and we're going to iteratively do that. If, for example, if we remove node A, we have to remove the connections from node A to E, F, B, D, G, and the FreeGraph function will do that for us. So let's create let's declare a function here. Let's use a function that we're going to create, FreeGraph. We're going to pass in our graph. And let's print here that we're freeing up our graph. Freeing up the whole graph. We're going to free the graph. And after that, let's print the graph. Print graph. And this should print that our graph has no nodes because it's pointing to null. And to make sure that graph is now back at pointing to null, let's print. So printing graph after it has been emptied, so you can print the pointer to the graph and check if it is equal to null. So we're going to print graph in here, and at the end we're going to return 0 if everything goes okay. And this is all we're going to need. So now we only have to do it, what we're left to do is creating the functions, and we're slowly going to test out these functions. So what I'm going to do now is, obviously, I'm going to comment out these functions that we're not going to use right now, and slowly incrementing back this this template for our main function after we implemented the functions that we need to use this, right? So let's just slowly add this. Sorry, let me just finish adding the comments. Sorry. So after adding all the comments, we're going to test the function. So we've just created our graph. Now we are able to print this, and now we have to create a PrintGraph function. So first function we're going to implement is the PrintGraph function. And so let's start by implementing the PrintGraph function. So to implement the print function here, or the PrintGraph function, let's hop onto the end of the file here. And let's create the template here. So this will be PrintGraph. This will receive a pointer to our graph that we'll call graph. And so the first thing we have to check if graph is equal to null, this means that our graph hasn't been initialized yet. So we have to print that our current graph has no nodes. And let's always print the name of the function as well, where the error or the message is coming from. So this is coming from PrintGraph. And we also have to return, right? So next up, what we have to do is we have to iterate through the whole list of pointers from our graph. And after each point, we have to call a function that will print the graph. And this function will be the print linked list. And this will be our helper function that will print the linked list that our pointer is pointing to. So in order to do that, so our graph next is different from null. Or I guess you can you could also say that our graph is different from null. But in this case, I want to do the last. If you do it like this, if the graph is different than null, all the loops will occur in here, and the printing will be the same. But it doesn't matter actually. So let's do it like this. I guess this is easier. We will avoid using many lines. So at each pointer we have. So if you come here at the slides, so we have a pointer to a linked list, right? And once we add node A, node B, node C, D, etc. Once we connect nodes, we'll have a linked list, and we want to print this, and then this, and then this. So we have to iterate through each linked list, and that's why we have a print linked list method that we're going to create called print linked list graph node name, because our graph node has two fields. It has the node name, that is the pointer to the linked list, and this is the linked list. And we also have a pointer to the next node that we're going to use to iterate. So let's say graph equals graph of next, because we have to iterate until we reach the end, right? And for that, we also have to let's also print a break line after each of this linked list has been printed, so we can see each of these on separate lines, as we're seeing here on the screen on the slides, right? So now what we're doing here, we're looping through this linked list of pointers, and at each pointer we're gonna call this function print linked list, and we're gonna print this linked list. After we're done, we're gonna go to the next pointer in our linked list and print the linked list it points to, and etc. That's what we're doing here. So this is basically our PrintGraph function. Now we have to create our print linked list function, right? And on our print linked list function, this will be very similar to this current function here. Difference being, it will receive a linked list that we call linked list, and we have to check as well if linked list equals to null. This will never happen in our case here, but if you're using this file and using this function in other places, it has a chance that you're printing a linked list that might be null. But in this case, we will always be printing linked lists that are they have elements within them. But it's good practice to try to foresee eventual problems that might occur if you try to print something that that doesn't have any elements. It's null. So that's why it's good to always try to catch edge cases like this. So current linked list is empty, And as always, let's print the function where this message is coming from. So this is coming from print linked list, and we return. And also we have to iterate through the whole linked list, and at the end, we're just gonna have the whole linked list printed. But in this case, as I want to print the last element in a different format compared to the others, I want to iterate up to the second to last element and print the last element at a different line. So what we're gonna do is, while linked list next is different from null, meaning that we're looping this until we reach the second to last element, and we're gonna print the character or the node name and a pointer pointing, meaning that it has another element coming. So it points to a different element, so it has a connection to something. And in this case, the connection is the linked list value, or the element in this case will be the value. And we have to loop, so we just say that linked list it's equal to linked list next. And at the end, once we reach the last element, we're just gonna print it by itself. This will be %s and linked list value. There's no need to print a break line here. This is because we have added the break line right over here. But you could add the break line over here if you wanted to, right? It makes a lot of sense. So if you don't want to add the break line here, what we can do is you can delete this line here and paste it over here. Or you can simply add right after this element here, and all of them will have the same effect, right? So this is basically the PrintGraph function that uses the print linked list function, and all we have to do now is test it. So let's first create the function declaration for these functions. So PrintGraph, let's declare it right over here. And I guess we're good. So let's clear this, let's compile it. So GCC undirected graph, no problems, let's execute it. And oh, we forgot to add a break line at the end here, but it's working as expected. So we're printing the graph before adding any nodes, and the result is current graph has no nodes, obviously, because the graph is empty, right? So let's go back to the file, and right over here, after each print statement, we want to add a break line. So it makes our lives easier to visualize stuff. So let's clear this, let's compile it again and run it. So as expected, same behavior. Let's go back to the file. And the next function we're going to have to implement is the AddNode function. So we can add values to the graph, right? So let's start implementing the AddNode function. So let's go to the end of the file and start implementing the AddNode function. So void AddNode. This will receive a double pointer to a graph, so a reference to the graph, and a character node. That will be the name of the node we're going to add to the graph. And in here, let's create an alias called graph. That will be the dereference of p to make our lives a little bit easier to use it. And every time we have to check if graph is equal to null. And if it is, in this case, if the graph is equal to null, we don't have to print anything because we're adding a node to an uninitialized graph. So the first thing we have to do is initialize this graph with a function that we create called initGraph node. So initGraph node. Let's pass in the graph we want to initialize and the node we want to add in this graph. And after we add this node, we just return. So after that, we're gonna have to add a new node to an initialized graph, meaning that if the graph is not null, it has been already initialized. We're just going to add new nodes to this graph. But first, let's create this initGraph node function. So let's hop up over here. So void, where is it? Void initGraph node. This will receive a reference to a graph and a character, or reference to a pointer to a graph, and the node we want to initialize the graph with. Let's also create an alias, ugraph graph equals to the dereference of p. And let's also create another helper variable here called temp. This will be a pointer to a graph, and this will be the node. We're going to allocate memory to create a node to this graph, and that's why I'm creating a variable, and this will be casted to ugraph. We're going to allocate memory, the size of ugraph. And if our variable temp equals to null, it means that our malloc has failed and we have to tell the user. So error in malloc. In this case, the function is initGraph. And let's add a break line. And if something goes wrong, we just return, right? If everything is fine, we're just gonna initialize the variable here. So node name will be equal to null, because node name, we're creating we're instantiating the allocating memory to a node for the graph, and the graph only holds a pointer. If you take a look here, we're instantiating one of these, graph pointer 1, for example. We're instantiating graph pointer 1, and it has the graph pointer 1 has a value, it holds a value that is a pointer to a linked list, but we haven't initialized the linked list yet. That's why we're going to have to create a linked list and initialize the linked list with the value we want. In this case, will be the value of node we're passing here. So that's why we're going to initialize node name with null. So this is our pointer to our linked list. Will be pointing to null until we initialize the linked list, and then we're going to change the pointer to the new linked list. So in this case, that's why we're going to have to create a function called init linked list. This is our helper function. And what linked list we're going to initialize? We're going to initialize the linked list that is pointing to temp node name, right? It's currently pointing to null, but we want to initialize this linked list because this will be pointing to this linked list, and we want to initialize with the value of node. And after that, the temp next, this points to GP1 points to GP2, that points to GP3, and etc. So our next will be equals to null because this is the first node in the graph. So next equals to null because this is the only node in the graph. It doesn't have any nodes to point to. And at the end, all you have to do is say that our pointer will be equal to temp. This means that our pointer P here, that is the original graph pointer we've passed in this function, will now be pointing to this new allocated piece of memory. This will be pointing to GP1, and GP1 is pointing to this linked list of connections here. In this case, we'll only have the first node. In this case, will be node A because we're going to initialize with node A. So now we have to create this init linked list function. So void init linked list, and this will now receive a pointer to a linked list, or the address of the pointer to a linked list, and a character called value, because in a linked list, we're not storing nodes per se. We're storing values because if you take a look here at the top, the linked list has a value. It doesn't have a node, right? That's why we're creating the name here as value instead of node. But you could call it whatever you want. That's why. But I'm going to keep it value here. So now let's create an alias called linked list. That will be the dereference of P to make our lives easier. As always, even though this in this case, this will be used, but there could be a case that this wouldn't be used. And in this case here, we want to initialize the linked list. So this pointer will be pointing to null. And we have to check if this pointer is not pointing to null because we cannot initialize an already initialized linked list. So that's why we're going to check if linked list is different from null, because we're initializing something. And if we try to initialize something that has already been initialized, doesn't make any sense, right? So that's why we're going to print to the user that this is an already initialized linked list, and this is coming from init linked list, right? Oh, sorry, this is at the end, and we just return, right? Otherwise, if it is an uninitialized linked list, we're gonna create a variable called temp that will be holding the allocation of memory for our linked list. So we're allocating memory for linked list and converting it back to linked list because this malloc hours return null, hours return void pointer, so we just have to cast it to linked list. And we also have to check if temp is equal to null, meaning that the malloc has failed. So we're also going to print error in malloc. In this case, this is init linked list. And we also have to return, otherwise we're just going to initialize it. So the value of our first node in our linked list will be value that we've passed through this argument here in the init linked list. And the next node doesn't exist because this is the first node. That's why next will be pointing to null first. And at the end, we have to get our original pointer to be pointing to temp, because temp is only a temporary variable that we used to create to make the allocation of memory here. And now the original pointer to linked list will be pointing to the same memory address of temp here. So we're done with init linked list, init graph node, and add node. At least the part where we're initializing the graph, right? If you try to add a node with only this function here, it will only work if the graph has not been initialized. So let's first try to add a value to the graph. Oh, sorry, this shouldn't be uncommented. So let's add the node A to the graph, and let's first declare this function here, create a function declaration. Sorry. There you go. So now we can test it out. Let me just check if, oh sorry, wrong file. Let me just check if the print graph is over here. Yes, it is. So let's recompile this and run it. And as you can see, we've successfully managed to print our graph that currently has only the first A node. If you take a look here, this is our current graph. We have a pointer to a linked list that only has the value A. And if you try to add another node to our graph, it won't work because this only works because it's the first node. We have to create the logic to how we're going to add new nodes to the graph if the graph has already been initialized. That's what we're going to do here. So let's hop onto the file again and continue this function AddNode. And to do that, the first thing we want to do is we want to create here a pointer called auxiliary. I'll call it aux for short for auxiliary, that will point to the same memory address of graph. And the reason I'm doing this is because we're going to use auxiliary to loop through the variables here. And we always want to add to the end of the linked list. So we have to loop through the whole list of pointers, and we're going to add to the end. We're not going to add to the start of our pointer linked list. So every time we add a node, we're going to add to the end of the graph of pointers. So as we only have one element here, we're just gonna loop through one element, and we're gonna add at the end of this one element. After we add B, for example, we're gonna loop through A and add B at the end. So while aux next is different from null, we're gonna check if the node is already in the graph, because as I stated before, we cannot add a node that is already in the graph. It doesn't make any sense. That's why we're not gonna add if the node is already in the graph. So let's comment here, check if node already exists in the graph. And if so, do not add node. So the check is pretty simple. So if at some point looping through the nodes here, aux node name value. Why we're doing this? Because aux is our pointer, and we have to point to the linked list and find the value. So that's why we're pointing to the linked list and find the value. So we can compare this value, if for example A, B, etc. If this value, if we find the value we want to add in our current graph, so if this is equal to node, meaning that this value is already present in the graph, we should not be adding this. So we have to tell the user that node, let's print the node like this, already present in the current graph. So, and let's print the name of the function where this message is coming from, add node, break line, and in here we have to return. Okay? And at the end here, we have to loop auxiliary. So aux equals aux next. Okay. So this is our first loop, and this loop will only go to the second to last element, right? This is the second to last element. Now, let's do the same thing and make sure that as we found the last element, we have to, in AddNode, I guess we can go up to the aux being, can aux be null in this case? So if aux goes up to null, no, aux next is different from null. If up to aux next, different. Yeah, we cannot make aux equal to null because we have to go to the last element and to point the last element to the next one. So we will have to do this. This will look kind of ugly, but let's do this anyway. So in this case, we'll copy everything inside here except the part where we're looping aux and paste it down here. And what we're gonna do is checking if node already exists in this case in the last. Oh, sorry, this is in the last position of the graph. If so, we're not gonna add it. And the reason we have to do this is because we have to loop until the second to last element, because if we loop up to the last element, this is the last element. If we go to aux equals to null, we will not be able to point the last element to the current element we're going to add. So we have to do this check after the loop again. And in this case, this is pretty simple. It is the same thing. We're just going to check if the current last node value is equal to node. If so, we're just going to print that it is already in the graph, and we're just going to return. And I forgot to add semicolons after return here. And last but not least, the last thing we have to do is add the node to the graph. So init graph node that we have already created, and we have to pass the graph we want to add it. And this is pretty tricky if you're not paying attention. We're not gonna add it to graph because we were not looping graph. We're looping auxiliary in this case, right? So in this case, we're gonna loop aux, next, and node. So what we're doing here is we're literally going to the second to last element, and we're gonna add a new node after the second to last element. So we're gonna create a node at the end of the linked list, and we're gonna add or pass the value node as we did in here, right? This is what we've done here. We're doing the same thing down here, right? Coming to think of it, I don't know if creating an aux variable makes any sense in this case. Does it? Doesn't make any sense because graph pointing to p. I guess we can simply delete aux in this case. So let's substitute here. Substitute everything from line 3, or sorry, from line 153 to line 156, 166, 167. Let's substitute everything that is aux with graph. Does it make any sense? Am I doing it right? I don't know. Let me check here real quick. It was supposed to be this, right? So 156, or is it this? 156 to line 167 %s aux. Oh, I guess this is the how you do it. Aux and graph, right? No trailing characters. Is it like this? What am I doing wrong, Eddie? I don't know, for real. Let's try this. Yeah, I don't know what's going on, man. I think I'm forgetting something in the syntax. Anyway, I think we can delete this, and everywhere where we have aux, we can call it graph. I was tripping for creating an auxiliary variable because I thought we would have to use graph somewhere else in this function, and I guess we don't. So in this case, doesn't make any sense, right? And here graph as well. Guess we good. No, and of course at the end here, we have to print what we want to print here. In this case, we're printing the node, right? We're printing the node, and here as well, we're also printing the node. I guess we're good, and now we can go to the main function again, and now let's add the node B and see if we can print it properly. So let's recompile it and run it, and yeah, it's working now. So the logic for adding nodes, it's basically complete. We can add as many nodes as we like. So now let's hop onto the file and keep adding nodes so we can test it out. So this, let's add node C. After we add node C, we're trying to add node C again, and this is pretty important. This shouldn't be allowed, and because of that, once we try to add node C and add node C again, this should state that node C is already present in the graph. So let's do this and this, and so adding node A, adding node B, adding node C, and then adding node C again. So node C already present in the current graph, and node C has not been added again. It's working as expected, and let's just finish adding the rest of the where is it, 40. Okay, we can go here, and we can finish adding the nodes to the graphs here. Why is it like this? Okay, so now that our AddNode function is complete, we can basically add all the nodes to the graph. And why is it here? It should be here, right? Bro. Is it okay? What is going on? Okay. Okay, so this works. So let's clear. So now what we're doing is we're creating, sorry, let's recompile it and run it. Recompile it and run it. And now we have added all the nodes to the graph. So node A to node H. If you take a look here at the slides, we've basically done this. We added node A, B, C, D, E, F, G, and H. Now we have the whole graph pointing to linked lists that only have the head node, meaning that they're pointing to the nodes themselves. They're nodes alone. So if you want to make a parallel, this is the current graph we have. We have all the nodes in the graph, but none of the nodes are connected. So now let's start connecting the nodes. And for that, we're going to have to create the ConnectNode method. So let me just go back to the slide where we have all the nodes, and we're going to add the connection with the ConnectNodes. So let's go back here, hop onto the file, and let's now create the ConnectNode function. So let's go back to the end of the file and create the function here, connect nodes. This will have the graph, and as we want to connect two nodes, this will receive node 1, and this will also receive node 2. And we also have to check if we're connecting a node in a null graph. So if graph is equal to null, we have to print to the user that current graph has no nodes, and this is coming from ConnectNodes, sorry. And after that, we just have to return. And now we're going to effectively connect the nodes. And for that, I'm going to create another function called AddConnection linked list. So AddConnection linked list. Sorry, I forgot to add some of the methods that we're using here in the slides, but I'll explain why we're doing this, because when we're connecting nodes, we're going to have to connect node A to B and node B to A. So creating a function called ConnectNodes and a helper function that connect two nodes, effectively meaning that we're going to add in the linked list of node 1 the node 2 at the end, and we're just going to have to pass node 1 and node 2 to this function first. So imagine we're connecting node A to B, right? So we're connecting node 1, that is A, and node B, that is node 2. And now we're also going to have to connect node B to node A in the list of node B. So that's why adding this helper function connect nodes using this add connection list. So this will be effectively the function that will actually connect or add a value to our linked list, and we're just going to have to call it on node 1 to node 2 and node 2 to node 1. So this will create this behavior here. So when we're calling add connection linked list node 1 to node 2, node 1 being A and node 2 being B, we're adding B to the linked list of A. And in the second line here, we're adding A to the linked list of B. So we're adding A to the linked list of B, right? So now we're going to have to create this function called add connection linked list. So let's create here. Void add connection linked list your graph. This will also receive our graph. Also, we're going to receive node 1 and node 2 because we're going to have to connect this 2. And the way we're going to do this, we're going to use flags, 2 flags, one for each node, while we're looping through the whole graph trying to find those nodes. Because as I stated before, if you're trying to connect to nodes, you have to check if the nodes actually exist in the current graph. Otherwise, we have to quit, right? There's no point connecting one node to something that doesn't exist. And to avoid creating a function that will loop through the whole graph, searching for a single node and then doing that for the second node every time we add a node, it's way more efficient to loop once through the graph, find where each node is, and if both nodes are there, we're gonna turn on flags 1 and flags 2 to tell the program that we found the 2 nodes we want to connect in the current graph. And then we're gonna add we're gonna effectively add these two elements together. But the thing is, we'll only loop through the whole graph once to find if either of these actually exists. If flag 1 or flag 2 keeps being 0, means that we haven't found one of the elements, and then we're going to print to the user that one of the elements in the graph, or one of the nodes we're trying to connect, does not exist in the current graph. So that's why we're going to do this. So int, let's create a flag node 1 equals 0, and int flag node2 equals 0. And let's create the two pointers to graph for node 1 pointing to null, and second pointer to the graph, node 2 pointing to null as well. So these will, once we find the first node in the graph and the second node, we're going to store them in these two variables here. That's why we're creating this, because we're only going to add one to the other if we find both. Okay, if we find both. In this case, so let's while graph, where is it? While graph is different from null, we have to check. So first, we're looping through the whole graph of pointers, right? And looking at each value that it points to, the head. So we're looking at the nodes here. So if the graph, again, node name, so we're looking to the value of node name because we're looking to the head of the linked list. If this is equal to node 1, in this case, we're going to set flag node 1 to be equal to 1 because we found node 1 in the current graph, and node 1 will be equal to graph. And if graph node name value equals to node 2, we're going to set the flag node 2 to equals to 1. And let me just check something real quick. I guess we don't even have to create this this second pointer here. The main reason being we only need to save n1 because we're not going to use n2 in this case, right? n2 is useless because we're just going to pass the node 2 name to connect to node 1, and that's why we're not gonna actually use node 1 in here. Okay, so we're just gonna set flag node 2 to equals to 1, and if we reach a point where both flag node 1 is 1 and the flag node 2 is 1, meaning that we found both nodes in the same graph, then we're gonna create a function that we're gonna call a function that will add these two connections together, and then essentially what we're doing is first we're adding a b to the end of linked list of a if we're connecting a to b. So if we're adding a value to the end of the linked list, let's call a function called add to end linked list. It makes a lot of sense, right? That's what we're essentially doing. And we're gonna add to each linked list, or we're gonna add this too. So we're gonna add to where we found a. So this is the linked list of a. N1 is the linked list of a. So we're gonna pass it by reference, and we're gonna pass the linked list itself because this is the pointer that holds. This is the structure that holds the pointer to the linked list. So the N1 node name will be our GP1, right? This is essentially what we're doing here. And then we're going to add to the end of this linked list the value node 2. And node 2 is the value B, right? So this is what we're doing here. After that, we just return because we've added. If not, we also have to make sure that we're looping, right? So in order to make sure we're actually looping, graph will be equal to graph next, right? This is essentially what we're doing to loop. If we reach a point where we reach the end of the file, or reach the end of the graph, and either flag 1 or flag 2 are not equal to 1, we're gonna have to print to the user that one of these or both are not present in the graph. So if flag node 1 is equal to 0, meaning that we haven't found node A, for example, we're gonna print to the user there is no such node A, for example, in the current graph. And the function that this is coming from is AddConnection linked list. Okay, and we have to pass in the node. In this case, this is node 1, right? So that's why we're gonna print node 1, and we just print. And also we have to do this if we don't find node 2, because there might be a case where both are not in the. We're trying for some reason the user tries to connect two nodes and both are not in the current graph, and then we have to print that both nodes are not in the current graph. So let's just save it. So okay, so we're good up to now. We're good. So we've essentially created the function called AddConnectionList. All the edge cases are being treated here, and now we have to implement the add to end of the linked list function. And now let's do this. This will be the function that will add B to the end of the linked list A in this case. So this will be void add to end of linked list, and this will be linked list. This will receive a the memory address or a pointer to the pointer of linked list and a character value, because we're adding a value to the linked list. And as always, let's create a helper variable called linked list with the dereference of p. We're going to check if linked list is equal to null. If so, we're going to print to the user that this is uninitialized linked list, and this is coming from add to end linked list, and then we return. Otherwise, we're going to add a new node to the end of the linked list, and to do so, let's do the same thing as we did in the add node, for example, but in this case we're adding to the linked list of connections. We're going to add here. So what we have to do is, let me just check something real quick if this is going to work. Okay. So while, so let's loop through the whole linked list until we reach the end, and we're going to add until we reach the second to last element, so we can point the last element to the next one we're going to allocate. So while our linked list next is different from null, we're going to check if the connection already exists, because as we stated before, if we loop through the whole list and we find the value we're trying to add, meaning that the value has already been added to the list or to the linked list, meaning that this connection already exists, there's no point in adding this connection again. So that's why we're going to print to the user that this connection already exists, and we're going to quit the loop. So if we find that linked list value at some point is equal to the value we're trying to add to the linked list, we're going to print to the user the connection from node, in this case node A, or to node B, for example, to node B, already exists. And this is coming from add to end linked list. Okay. Let's add a semicolon and return if this is true. Otherwise, we're just gonna keep looping. So temp, or not temp, sorry, linked list equals linked list next, right? So we're just gonna loop until we find the last element. And if we don't find the value we're trying to add at the end, we also, as we're looping up to the second to last element, we also have to check if this is true for the last element again. So if linked list value is equal to value, the connection from something to something already exists, and we return again. So the connection in here is from the node we're trying to add, so the head of the linked list. So in this case, the head of the linked list is the, we can call it P value. I'm not using linked list value here because we're using linked list to loop through the whole list, right? It doesn't make any sense to use linked list here because this is no longer pointing to the head. This is pointing to the head, and so this is the head. So A and B, for example, and the B is the value we're trying to add, right? So linked list and value, and the same thing applies here. So this will be from P, from the reference of P value up to value. So from A to B again, and let's save it so we can parse the file. Okay, so now that we have added the checks to check if a connection already exists, if we pass these checks, meaning that we're gonna add the connection, we're gonna effectively add the connection. So let's just comment here at what we're doing here, checking if the last element is the existing connection, and of course on top here, this is checking if connection already exists. Okay, so now we're going to effectively create a new node. I'll call it temp. This will be this will be linked list. Where is it? Linked list equals malloc. This will be malloc size of linked list. And we're also going to have to check if temp is equal to null. I'm going to print to the user that error in malloc. Again, in this case, the function is add to end linked list, and we return. Otherwise, everything went all right, and now we have to add the value of this allocated to be the value, and the next will be equal to null because we're adding to the end. And of course, the linked list next will be equal to temp. meaning that we're getting the second to last element, or in this case, this previous last element, and we're pointing it to the new element, to the new last element. And this is essentially what we have to do in order to create or to connect two nodes, catching all the edge cases when it comes to connecting nodes that have already a connection between them, and etc. So now all we have to do is test. Sorry. Before that, let's add the function declaration for these connect nodes over here, and add right here a node type ugraph. Oh, it's ugraph. Sorry. And over here the same thing. It's ugraph. And let's uncomment the lines where we're actually adding connections to see if it's working. And I'm gonna uncomment all the lines that have to do with the connection so we can clearly see it together. What is this? Sorry, exist in. Okay, I guess this is fine. And also we're gonna add the connection. So adding connection between A and B, A and C. So, and we're gonna go through. Let's first test if it's working. So let's compile this and run it. So we had up to here when it comes to adding nodes to the graph. So our graph was like this. We had all the nodes. Once we had connections A to B, this is our graph. So this is working as expected, right? We've connected A to B, and we also have a connection from B to A, of course. And after that, we would connect A to D, but in this case I'm creating a virtual connection from A to C so we can test later on when we implement the RemoveConnection function. We're creating a connection from A to C. That's why we see here a C to the end of the linked list of A and a to the linked list of C, meaning that these two are connected. And also I'm trying to create a connection between a node A and a node K, and K does not exist in the current graph. So that's why it's telling me here connection from A to B already exists. Oh, sorry. I guess this is not the error message we're looking for. Let me go back here and check if this was the intended behavior. Oh, I guess I forgot to change here in the. Okay, there we go. Between A and K, right? Where is it? A and K, and that's why this is A and B. This is A and K. Okay. Now let's recompile it and run it. And now it has the expected behavior. So adding the connection between A and K, and now it's telling me that there is no such connection, there's no such node K in the current graph, and it's telling me twice because I'm trying to connect A to K and then K to A, as I stated before. Because when we try to connect two nodes, we have to add one connection to the first and one connection to the second one. And up to now, everything is working as expected. So we have finished the implementation of our ConnectNodes method, and it works. So let's now just finish connecting everything. Oh, sorry, wrong file again. Now let's test. Let's finish printing all the possible connections. And in this case, why is it in this line? Okay, for some reason it jumped between two different lines. Okay, so let's go to the end of this line here. Add a single quote here. And here as well. Okay. So connect nodes. This is also connect nodes. Connect nodes and PrintGraph. So what we're gonna do here now is we're gonna add all the connections that we have to add to A, and we're gonna try to add a connection that already exists that we added here, A to E, and we're gonna try to connect A to E again. We accidentally tested it out when we mistyped A and B, and it printed out that there was a connection between A and B, but we're just gonna test it for test sake here in this case. Let's just uncomment all these connect nodes again, because this is we're just essentially connecting everything. Oh, and this is remove connection, so we don't want to mess with it right now. And let me just fix it again, because for some reason this has gone to a different line, and this as well. Let me just go to the end here and add this. Let's recompile this and run it. Okay, so up to here, add nodes to the graph. We've connected A and B, connected A and C. This is a virtual connection that will not exist at the end of the file, because the next step will be removing the connection from A to C. Try to connect A and K. K does not exist in the current graph. That's fine. We're adding D connections to A, D, E, F, and G, and that's why now A has all these connections. And all the nodes from B to G have A in their linked list because they have a connection. Because if you take a look here, uh, if you let's go back here to the graph. This is essentially what we have, except that we have a connection from A to C now that shouldn't exist because we're going to remove after we implement the remove connection. But this is essentially what we have: A connected to B, D, E, F, and G. So B, D, E, F, and G, and also C here that we're going to remove. And after that, we're going to add all the connections between B, so B, C, F, G, and H. So B, C, F, G, and H. That's why B has all these connections, C, F, G, and H. And now C is also connected to B. F is also connected to B. And G is also connected to B. So this is the current state of our graph. If we take a look here, where everything has a connection to B. So this should be the state of our graph, except that we, as I stated before, we have a connection between A and C that shouldn't exist. You just have to ignore here, but this is the state of our current graph, removing the connection from A to C. And last but not least, we added the connections between F, G, and H. So this would be our complete graph. So this is the final graph representation. This is our final graph representation as well. The only difference is that we also have an extra connection between A and C again. So now let's implement the remove connection so we can actually remove this connection, test the remove connection method, and actually have the same graph we have here. So let's hop onto the file. So now let's hop onto the end of the file here and create our void remove connection function here. Let's create, it will receive a graph or the pointer to our pointer to the graph, and the node we want to remove are the connection first from the node 1, and the second node we want to remove the connection to the node 2. Okay, oh sorry, node 2. In here again, let's create an alias ugraph equals to the dereference of P. I don't know why I added in parentheses, but anyway, it doesn't make any difference. And again, checking if graph equals to null, just to make sure this is an initialized graph. The current graph has no nodes, and this is coming from remove connection, and we return. So in order to do so, we also have to check if we're removing a connection between two nodes that actually exist in the graph. At least the two nodes have to exist, and if at least one node does not exist, we're going to have to quit the remove function and print to the user that one of the nodes does not exist in the current graph. So in order to do so, let's also use the same idea as we used before in the AddNode function. We're going to create flags, and in this case, the flags will be once we're looping through the graph pointer. So we're going to loop through this linked list of pointers and looking at the head value. And we're going to have to check if the elements we're trying to disconnect are actually in the graph. And doing this with flags in only a single loop prevents us to actually having to create a function that loops through the whole graph looking for a single value. And if it doesn't find, we're going to have to look for the second value. We're just going to do it once. And if we find both values, we remove. If we don't find one of the values, we just tell the user one of the values is not in the current graph. So in order to do so, let's also create again the flag node 1. And this will be equal to 0. And int flag node 2, starting at 0. And in this case, we're going to have to create two helper pointers, because we have to remove the connection from N1 to node 2 and from N2 to node 1. So that's why we are also, in this case, we're actually going to need 2 pointers. So the pointer that will hold the value for node 1 and the pointer that will hold value for node 2, both starting at null. And now we're going to loop through the graph. So our graph is different from null because we can loop through the whole graph, no problem. As we're not adding anything, we're not messing with the linked list of pointers. We're messing with this. We can loop through the end until it's null, because we're not adding or removing anything from this first linked list. We're going to mess with the linked list that they are pointing to. So in this case, we're going to check if graph node name, again, node name value, because we're looking to the head here. So graph node name is the pointer to the linked list. So we're looking at the value of this linked list, so we can have a look at all the nodes in the linked list. And if this is equal to node 1, meaning that we found node 1 in the graph, we're gonna add the flag node 1 to be equal to 1 and n1 to be equal to graph. And we're gonna have to do the same thing for node 2. So let's copy and paste this. So in this case, if we find node 2, we're gonna have to change the flag node 2 to 1, and we're gonna save node 2, our pointer, to node 2 to equal to graph. And if flag node 1 is equal to 1 and flag node 2 is equal to 1, meaning that both nodes are present in the graph, we're going to remove them from the list. And as we're going to remove from the linked list, so we're going to remove the connection from node 1. So imagine we want to disconnect C in the we want to disconnect A to G in this example, because we don't have the A to C connection here that we're going to remove. But if we want to disconnect A to G, N1 will represent this pointer that is pointing to this first linked list and holding value A, and we want to disconnect node 2, that is G. We're going to remove this from the linked list, okay? And also, we're going to have to remove the connection A from the G, because if we add to both, we have to remove from both, okay? So the connection between them no longer exists. So let's create a function called remove from linked list, because in this case, we're removing from the linked list, not from the graph. And we're going to remove first from, in this case, A to C in our example. So A to C, and A, this is the linked list. So the N1 pointer points to the GP1, and the node name field is the linked list itself. It is the pointer to the linked list. And then we're gonna remove the connection from A to G, right? In this case, A to C in our example here, because we're gonna actually do this. And remove from linked list. We're gonna remove now from node 2. So N2 is GP7 in this case of A and G, and the node name field, it represents the G here, or the linked list that starts with G, that is pointing to G. And node 1, we're going to search this linked list for node 1, meaning the connection A, and we're going to remove this guy from here. So we're removing G from A and A from G. In this case, will be C from A and A from C in our example. Okay, and after we remove it, we just return. And of course, we have to loop through the graph. This is a loop, right? So we can look at each header and see if we find the nodes we're trying to disconnect from each other. And graph will be equal to graph next. And if we reach the end of the loop and we didn't find anything, it means that one of the nodes is not present in the graph. And we can simply print to the user that no connection between nodes A and C, for example, or A and K. And this message is coming from RemoveConnection again. And we're also going to have to print node 1 and node 2. And we're basically done with the RemoveConnection function. Now we have to implement the remove from linked list function. So let's hop here, void remove linked list, remove from linked list, remove from linked list. And this function will receive a pointer to the linked list and a character node, or in this case, let's call it value because we're removing from the linked list, right? And let's create again an alias. Linked list will be equal to P, or to the dereference of P. Again, checking if linked list is equal to null. If so, we're just going to print to the user that current linked list is empty, and this is from remove from linked list, and we return. Okay. Otherwise, what we have to do is we have to loop through this whole linked list. So say we want to remove G, we have to loop through this whole linked list, find G, and remove this element. And if it is in the middle, we have to go up to the second to last element, remove G, and point this element to the next. So in this case, F will be pointing to the next of G. In this case, it's null because it is the last element. So in our case, C is right here. So we remove C, point A to B. That's what we're going to do, right? So we have to loop through the whole list until we find the element. And we're going to loop until linked list next is different from null. And we have to make sure that if linked list next value, so in this case, we're always looking to the next element and checking the value of the next element. If it is equal to our thing, if it is equal to our node we want to remove, we're actually going to do the remove. The removal, because we want to keep our pointer pointing always to the previous element of the element we're going to remove, so we can change this pointer to the next pointer. We don't miss the reference of the last element, right? Because there's no connection back, there's only connection forward. We cannot go backwards in this linked list implementation. Okay, so in this case, if we find this element, let's create a temporary variable called temp. This will hold the variable, the value of the next element, or this will be pointing to the next element. So in this case, we'll be pointing to G in this example here. And to save this reference, right? And linked list next will be pointing to the next of temp. So what we're doing here is linked list is at F, and we're pointing to the next of temp, and temp is at G. So we're pointing at next of G. This is equal to no. So F will now be pointing to no. And now we're free to remove G because there's no reference to G. So in this case, we can free temp with no problems, and then return after we finish removing. After we finish removing this element. And of course, we have to create, actually loop the elements here. So linked list will be equal to linked list next. And if we reach the end of the loop and we haven't removed the element, let's print here to the user, no node named, in this case, K. For example, if trying to remove A from K, no node named K to remove from linked list, because of course there's no connection between A and K. We're trying to find K in the list that doesn't exist, and the K doesn't exist. So, and this is coming from remove from linked list, and we're also gonna have to print the node we're trying to find that we didn't find. And yeah, this is essentially all we have to do for the remove connection. And I guess we're good. Now all we have to do is, oh sorry, in this case it's not node, right? I got caught up in using node instead of using value, because now we're in linked list. Now we're supposed to be using value keyword. That's the standard we've been using throughout the whole code here. So let's use value here. So yeah, the only thing we have to do now is go back to the top of the file and create the function declaration for the remove connection. And we actually have to test the remove connection here. So let's remove these lines and print the graph after remove connection from A to C. Let's clear this, run it, and this is the graph, the last graph we found after we've done all the connections. And there is an imposter connection here compared to our graph, as we stated before. This doesn't have any connections from A to C and from C to A. And we have to remove this A to C and have to remove this C to A. And after we remove the connection from A to C, we get to the exact same graph we're seeing here. There's no more connection between A and C, and no more connection between C and A. And now we have the perfect graph for our example here. And now the remove connection function is actually working properly. And yeah, that's basically it. The remove connection function is working as intended. Now we have to create the last function we want to test. And if you take a look here at our main function. Oh, sorry. We also have to test the connection between trying to remove a connection from A to K, and K does not exist, right? K is not in the present. What is it called? K is not present in the current graph, so there's no connection between A and K. So let's run it and here it is. Trying to remove connection from removing the connection between nodes A and K does not exist in the current graph, so no connection between nodes A and K. And I forgot to print the graph after we try to remove this connection. Let me just grab this line here and print right over here, so we can clearly see that nothing changed in the graph. So once we're trying to remove a connection from A to K and K does not exist, the connection between A and K, there's no connection, right? Because K does not exist in the graph, and that's why the graph remains the exact same. And there's one more test we can do. This is trying to remove a connection from A to C. And the thing is, C is not, let's try to double remove the connection from A to C. So let's print it here. Trying to double remove the connection between nodes A and see what we get. This will be on top of the K here. So if you take a look here, removing the connection from A to C worked in the first place, because A had a connection to C and C had a connection to A. When we first remove it, it works as intended, so A has no longer a connection to C and C has no longer a connection to A. And when we try to double remove the connection from A to C, no node named C to remove from the linked list, because A has no connection to C, and no node named A to remove from the linked list because there's no connection from C to A, and this is the intended behavior. Nothing has changed in the graph. And again, when trying to remove connection from A to K does not exist. Nothing has changed in the graph, and it says that no connection between nodes A and K. So everything working as expected for our function. Remove connection. And now the only function that we have to implement now is the FreeGraph, and the FreeGraph will be using the remove node because now we're going to be removing nodes from the graph, and now we can test the remove node within the FreeGraph. FreeGraph only loops the whole graph using the remove node function, and that's why I'm not using the remove node function in the main function, but you could try yourself. So let's now move on to the implementation of the FreeGraph function. So hopping onto the end of the file again, let's create here our void FreeGraph function. This is our ugraph. This will receive our pointer to the undirected graph, and this is all we have to pass to this function as an argument. Again, creating an alias called graph, points to the dereference of P, and again checking if graph is equal to null to print to the user that current graph has no nodes, and this is coming from FreeGraph. Jump line, return. And here, what we have to do is, if the graph is not null, meaning that it is initialized, we have to free all the nodes or remove all the nodes. And in order to do so, we can, let me see what would be the best option here. We could, if we want, we could create a helper variable. Let me just check if it makes sense to create a helper variable. So, yeah, in this case, what we're gonna do is, let me hop onto here. Imagine we want to free the whole graph. We have to loop through the whole graph until graph is equal to null, and we have to keep a reference to the next element. So once we free, imagine our graph variable is pointing to GP1. Once we free this guy, we have no more reference to go to the next element of graph because graph was pointing to this guy. We freed up this guy. There's no more reference to GP2, and we have to create a reference to this guy beforehand, and then we free this guy, and this can be done using a helper variable. So that's why I'm gonna do this. So let's create here a ugraph variable. This will be a pointer to a graph. We call auxiliary, and this will hold the value of the next element. So we can always have a reference back to the next element. So if graph is at GP1, we're saving auxiliary pointing to GP2. So after we free GP1, we can say that auxiliary, our graph points to GP2, and our auxiliary points to the next of GP2, so GP3, and we can iteratively do this until we free the whole graph. So that's why we're going to need this auxiliary variable here. And while graph is our graph next, in this case, is different from null, meaning that we're going to go up to the second to last element, and once we reach the end, we're just going to free the last element at the end, because if we go up to the last element in this loop, once we reach GP8, auxiliary will be trying to point to the next of GP8, and this will give us a segfault because GP8 is pointing to null, right? It doesn't make any sense. I guess we could try to point because GP8 points to null, so auxiliary points to next of GP8. But in this case, our graph is going up to null, right? Yeah, our graph is pointing up to null. So null has no next. In this case, let's keep it like this. So we're going up to the second to last, we're going up to the last element in this case, and we're going to stop at the second to last element, and we're going to print here to the user which node we're freeing, so we can see in the screen, freeing up node S in this case. Let's add a break line here, and the node we're freeing is the graph node name value. So this is the head of the node we're freeing here. And the way we're going to free this is by using the function called RemoveNode that we stated before. We're going to test in here. And RemoveNode function will receive a pointer to the graph. So P, it will have the same reference here. And and it has to receive the node we want to remove. In this case, is the graph node name value. So this is the element we want to remove from the graph. And then graph, after remove node frees up this node, graph has no more reference to the next element. That's why we've created this auxiliary variable. So now graph will be pointing to aux, and aux will be pointing to graph next. Okay, graph next. And then after we've done the deletion, we're gonna print the graph for the user. So let's see here, printing the graph after each iteration, so we can see the propagation on deletion. So we can actually follow up after we delete node A, what happens to the graph when we delete node A. We have to check if every single node that had a connection with A no longer has a connection with A, and that's why we're gonna print the node or print the graph after each iteration of deletion here. So let's print graph, and at the end, so this loop will allow us to remove every single node up to the second to last, but we also have to remove the last node, and that's what we're gonna do here. So remove node, again in the graph node name value, and this is all we have to do, and we're gonna print the graph after the last node has been removed on the main function. So there's no need here to add a PrintGraph function down here. So we're good up to now. This is the FreeGraph function. It holds all the edge cases we need, and now the only thing we have to do is actually create a RemoveNode function that will do the job for us. So let's create a void remove node. This will receive a ugraph pointer to the pointer, and the value we want to remove, in this case the node, the char node we want to remove, right? And again, let's copy down here. I don't want to type it again. I've typed this too many times. So we're also going to create an alias, check if it is null. If it is null, meaning that the graph is empty, we're going to tell to the user that graph has no node, and this is coming from remove node, right? Remove node, and we're going to return. So now let's start with creating the logic that will actually allow us to remove everything. What we have to do is, once we remove a node, what we're essentially doing is we have to first clean the whole linked list this node is pointing to. So we have to free all the variables that are in the linked list this node is pointing to. So imagine we want to free the pointer or the node GP1 here. We would have to hop onto this linked list, free this whole linked list, make this pointer equal to null, and then make our pointer to GP1 point to GP2, and then free GP1. So we have to free the linked list and free the pointer and make sure that our original pointer points to the next element. And this is kind of a hassle because we don't have a header pointer in this linked list implementation. So we have to treat this edge case. And to do so, the first thing we have to do is check if the first node is the element we're looking for. And if it is, we're gonna use the pointer representation from or the dereference of P instead of using the graph variable. So we can say that the dereference of P will be pointing to GP2 instead of and then if it is not the first element, we're going to loop through the whole list and delete accordingly, right? So but as this linked list doesn't have a head, we have to deal with this hassle of actually checking if it is the first element. So we'll probably run into trouble in terms of segfault, because we'll be pointing to something that has no longer has allocated memory. So let's first treat this edge case. So if graph node name value equals to node, meaning that we're checking if the first element in the graph is equal to our node. That's what I'm saying here. If GP1 is equal to the value we're looking for here. So if A is the value we're looking for, so GP1 points to this value, right? So what we have to do here is create our helper variable here called temp to point it to a linked list, because we're going to clean the whole linked list. And this will be the graph node name. Because what we're doing here was we're creating a variable temp pointing to the linked list of this first node here. So temp is pointing to A, B, D, E, etc. And then we have to remove every single element within this linked list. And we know how to do this. We can loop through this whole linked list, removing all the connections. And to remove all the connections, it's pretty simple. So temp points to the linked list, and temp next. So while temp next is different from null, so we're looping up to the second to last element. And what we're going to do is we're going to remove connection, because we have this function already. This removes a connection. This basically deletes. If we pass here a graph we want to remove a connection from, we pass in the node we want to remove the connection from. In this case, we're moving a connection from node A to something. And this something is the value of the next variable. So what we're essentially doing is we're keeping temp pointing to the first element in this linked list, and we're saying that we want to remove the next element. We want to remove the connection from A to B, and after that, temp will be pointing to A, but now A will be pointing to D, and then we will remove the connection from A to D, and now A will be pointing to E, and now remove the connection from A to E, and etc. Until A has no longer any connections. That what we're essentially doing here. So we're removing connection from the graph, from node. So node obviously is held by this value here, A, and we want to remove the temp next value. So removing B, D, E, F, and G. And after that, there's only the A head node left to remove. And in order to do so, to remove this node, we're going to say that the graph node name will point to null, because we're going to free this value. So we point this guy to null, and then we say that temp is already pointing to A, and we free temp. And now the only thing left to do is now this whole linked list has been freed up. This guy is pointing to null. We have to free this guy. So now the only thing we have to do is say that P, our original pointer, the reference of P, will be pointing to graph next, so pointing to GP2, and then we free this guy. We free graph. That's all we have to do. So now graph node name is equal to null. We now free temp, so we're freeing the head node. And now the dereference of P that was pointing to the GP1 will now be pointing to graph next. Now this will be pointing to GP2. And now we can free graph with no problems, right? And after that, we just return. This is the hassle we have to go through, as we don't have a head node in this linked list, and we have to check if the node we're looking for is the first one. After we're done with this, we can use the same logic to remove remove a node if the node is in any other position other than the first position. So same thing here. If graph next is different from null, so while this is happening. So have I added here the loop? Oh, sorry. Where am I? Remove connection. Remove node. Okay. So let me just check here. Okay. So we're done with this. So now, while graph next is different from null, so we're going up to the second to last element, and we have to check if we have to find where is the node we want to remove, right? So if graph next node name next is equal to node. This is pretty confusing, right? So what we're doing here is, imagine we're looping through this linked list of pointers, right? This is essentially what we're doing here. And graph is pointing to GP1, for example. And now we're at GP2. And we always have to keep track of the last element and compare it to the next, because the same way we were doing removals from the linked list, we have to keep track of if the next value was the value we wanted to remove, because then we could switch this guy to point to the next of the guy we want to remove, and without having to create a backtracking option. That's why we always keep comparing if the next value is the value we're looking for. If it is, we set a temporary variable to this guy, point this guy to the next of the guy we want to remove, and then we free this guy up. The same thing we're doing here. So we're checking if the next node of the graph, so imagine we want to remove GP3. We are GP2. So we're checking if GP3, so GP3 node name value, so C, so we're checking if the next pointer header, or the next point head of the linked list, is the value we're looking for. If it is, then we're going to free this guy up. So we're going to free this whole linked list, and then we're going to say that GP2 will point to GP4 because we have a reference to GP2, and then we're going to free GP3 without any problems. This is kind of confusing, but this is the way it is. So now that we're looking, that we've explained what we're doing here, if this happens, so if we find the next element has the linked list with the head we're looking for to remove, we're going to perform this removal. So we're going to create a temporary variable called temp. This will equal to graph next node name, because again, our graph is pointing to GP2. We want to remove or free the linked list of the next element. So that's why temp is pointing to the next node name value here. So this is the next graph is pointing to GP2, and now temp will be pointing to this linked list holding C from GP3. Now we have to do the same thing we did before. So while temp next is different from null, we're going to call the function RemoveConnection, and it will work the same way. So we're going to have pass the graph, the node we want to remove, and in this case, the node we want to remove the connection is now temp will be pointing to C, for example. Temp will be pointing to C, and we're gonna remove recursively every single element as temp. We want to remove temp. Where is it? Temp next value. Temp will be always pointing to the head, and will be always removing the next element, and until we have no more elements. Once we have no more elements in the linked list, we only have the head. We're gonna have to free the head, and again, to free the head, same concept. So graph next node name. So graph is pointing to GP2. Now we're saying that graph next node name. So graph GP3. This pointer will be pointing to null. So this will be pointing. Oh, sorry, not to null. We'll be pointing to next of a temp. So temp next in this case, right? Sorry, does it make sense? Let me just check the logic. So graph will be pointing to next node. Oh, sorry, yeah. Let's set it to null first, because we have the reference here from aux here. There's no need to do this. So graph will be pointing to null. So GP3 will be pointing to null, because we're saying that the linked list, the pointer to the linked list will now be pointing to null, because we want to free this guy up, right? We want to free the head. That's why we have to get this GP3 pointer to point to null. Yeah, it's kind of confusing, but I guess you get the point. So graph is at GP2. We've said that temp is pointing at C. We've removed all the elements from linked list. Now we only have the head C. We have to remove C, and to do so, we have to get the reference from GP3 to C, that is node name, and point it to null, so we can free C without any problems of referencing. And then we remove this guy. Then we remove GP3. And before that, we're going to say that GP2 will be pointing to GP4. So in this case, we're just saying that the pointer of GP3 was pointing to C, will now be pointing to null. So we can free this guy up. So we can free temp. So temp was that variable. And now ugraph aux is equal to graph next. So what we're saying here is that we're creating a variable auxiliary that it is pointing to GP3, because we want to free GP3, because GP2 is graph. Auxiliary pointing to the graph next is pointing to GP3. And now we're going to say that graph will be equal to the auxiliary next, because we want to point to GP4 and then free GP3. So graph next will be pointing to auxiliary next, and then we're going to free GP3 in this case, free aux, and then we return. The way we've implemented this is kind of confusing, I'm not going to lie, but it is what it is. It works. So I lost here where I was. I moved the cursor here a little bit, and the file just chewed up, and I lost the cursor. Oh, so here it is. So after we remove the elements, we return, and then we have to loop. So graph equals graph next, as every loop in linked list. And if we reach the end of the function and we haven't returned anything, meaning that we haven't found a node, so we couldn't remove this node. So imagine we tried to remove node K. There's no node K in this graph to remove. So we looped through the whole list. We didn't find node K, meaning that we have to print to the user that there's no node K in the graph. So no node named in this case as in current graph. And this is coming from the function remove node. And we have to pass in the node that wasn't found in this case. And I guess this is everything we have to do. And ugraph here, sorry. This is the word ugraph. Okay. And this is remove connection, right? Remove connection. And comparison of distinct pointer types, structure node. And next, and this is value, sorry. Next value, right? So graph next node name, sorry, graph next node name value. This is the comparison we have to do, same thing as up here. So we're pretty much good to go. I think if we haven't done any mistakes here in this confusing logic, this should work. So let's test it out. So let's go down here and test this function. This is the last function we have to test. And let's create the function declaration for FreeGraph. Let's print it here. Let's clear, let's compile it and run it and see if we can get it. So yeah, it seems it works. So what we're doing here is let's take a look here at the last step we've reached So I think it was, yeah, I think it was removing the connection between nodes A and K. And of course, K doesn't exist, and there's no way to remove the connection. There's no connection between nodes A and K, and the graph is the same graph we had here. So A, B, D, E, F, and G. So as you can see, this is our graph, exact same graph representation. So we've managed to create AddNode Function, connect nodes, remove connection, and of course the free graph that has the implementation of the RemoveNode function as well. And if you see here the free function, the first node we're freeing is node A. So once we remove node A from the graph, we have to remove the connections that A had to all of these other variables here, to all of these other nodes, B, D, E, F, and G. So if you take a look here, A is no longer in the graph, and B no longer has a connection to A. Same thing goes to D, E, F, and G. So it works. So once we remove node B, so we free up node B, we have to remove all the references in C, F, G, and H. So C doesn't have anything. F doesn't have anything to do with B, G as well, and H as well. Now, removing node C, it has no connection, so we only remove node C. After that, we remove node D, so no connections here as well. After that, we remove node E, no connections as well. So this, we just actually pop the node. And after that, we reach the end where we have the F that has the last connections between other nodes. And after freeing F, we have to remove every relation F has to G and H. And of course, we're left only with G and H. That after we free up F free G, we only have H. After we free H, we print the graph that is empty. So that's why the prints current graph has no nodes. And after that, we print the pointer to the graph to actually check if it is pointing to no, and it is. So this video is quite long. I think this is a really good exercise in order for you to understand pointers and linked lists and how you can implement graphs, how these data structure works, and how you can implement a linked list that holds another linked list, as we've done here. This is one way you can implement a undirected graph. This is one implementation of graphs. As I stated before, there are many different graphs. You can try to mess around with this tutorial and try to implement a weighted graph or a directed graph. You can just mess in the structure of the linked list, and also mess in the structure of the functions we've created so far. And yeah, this is a pretty good experience. So let me just wrap up what we've done. So we added node A, B, C, D. So let's check here. So we added node A, B, C, D, E, F, G, and H. So here it is, no connections. After that, we started adding connections A to B. So A to B, A to D, A to E, A to F, A to D, and then BC, BF, BG, BH, FG, and FH. So this is the visual representation. If you take a look here, this is the graph we had after we added all the nodes. So the same thing here. And after we added the connection from A to B, that's what we have here, A to B and B to A, because it's an undirected graph. You have to, if you add connection in A, you have to also add the connection in the linked list of B. Same thing, AD. So in this case, we added the C connection here, but ignore it because we're gonna remove it later on. This is just for testing removal, and that's why we added A and C. It doesn't have here, but we'll check later on. So A and C and A, of course, and adding a connection between two nodes that doesn't exist, because it can't be. You can add a connection to something that doesn't exist. So that's why A and K, there's no such node K, and it pops up twice because we tried to add A and K and A. So that's why we have two feedbacks here, and nothing changes in the graph. And then we add the remaining connections D, E, F, and G to A. It pops out on every single thing here because we have to add it to every single one of these. Next up, we try to duplicate a connection between A and E that already exists up here, and it says that the connection from A to E already exists, and says it twice because, again, we try to connect A to E and E to A. Okay, and it doesn't change the graph because it's not allowed. And then we create all the connections from B to C, F, G, and H, as you can see here. Again, adding connections between F, G, and H, everything here. And this is almost the exact same graph we have after we add all the connections. The only difference is that we have an extra connection from A to C that we're gonna have to remove using the remove connection. And once we remove connections from A to C, there's no longer this connection from A to C that we had up here, and then no longer this connection that we had from C to A here. And this is the graph, the original graph that we have here. So you can pause the video and check. It is the same. And now we try to double remove the connection from A to C. And of course, there's no more connection between A to C. That's why no node named C when we try to remove connection from A to C, and no node named A because there's no more connection from C to A. So nothing to remove here. The graph stays the same when you try to remove a connection that does not exist. Next up, we try to remove a connection between A and K does not exist. Of course, you can't remove a connection from a node that doesn't exist. That's why it says no connection between nodes A and K. And last but not least, we try to start freeing up the graph, so completely remove node A, and everything that had connection. So A is no longer in the graph, and everything that had connection to A loses the connection to A. Once we remove node B, the same thing. B is no longer in the graph. Everything that had connection to B loses the connection with B. C, D, E, F, and F was the last thing that had connection. G and H lose connection to F. They are alone. Remove G, remain H. Remove H, no longer anything in the graph, so graph has no nodes. And then reprint the pointer to the graph. It's obviously pointing to null as expected. So this is it. I guess if you have any questions, you can post down in the comment down below. I'll try to answer them. This is a very extensive video, but I think it's pretty good if you have time to stop and understand what we've done here and try to implement it step by step in your own environment and try to add new things to the graph as I stated before. Try to make different implementations of graph. This is just one implementation, and I'll be bringing more videos about data structures and algorithms in the future as well. This was undirected graph, unrated graph as well. And thanks again for watching. I'll see you guys in a next video. Peace.